Okay.
I thought it was beta.
So we are going to take all of our Taylor polynomial knowledge and mash it together with our series knowledge.
Haven't we already been doing
I mean, independently, yes, but
Not in a big board.
I'm gonna laugh when I'm on the test. I miss all this Taylor the entire
Okay, so let's remind ourselves that a Maclaurin polynomial is when we center at 0 and we take f of 0 and then f prime of 0 times x and then f double prime of 0 over 2 factorial times x squared. Surely we can write this as a pattern, right? Okay, so for our series, we would write it like this. I would like you to copy down what this looks like because there will be times, especially on the AP type problems, where I ask you for like the first non-zero terms and the nth term. So write down the series and then write down this so you can see what this nth term kind of looks like. That's what this is called right here. Okay, and then we also have this for something not centered at 0. It's who knows what day it is because we've had such a weird schedule. Ugh.
Don't you love them snow days?
Used to. I didn't.
I enjoy them in small bits. Okay,
You get a snow
so
day of-
the key here is going to be finding a pattern for what our numerators would be, okay? So we can't really write like the kth derivative of 0 in our series. So we're actually going to have to do a little bit of thinking and make that look a little bit nicer. Okay, find a pattern for us to write there. And I'll show you what I mean when I get to it. But we need to essentially start making our Taylor or Maclaurin polynomial and use those patterns to write it as a series. Dave, you let me know when you're ready, okay? No, I.
What's our
What's our what?
code word?
Oh, what is our code word?
First day.
Alabama. What did you say?
First day.
Oh, and the
First
first day?
Little Sam from Alabama. That's what Emily is. What about a little lamb from Thursday?
Wrong.
There it is. Little lamb from Thursday. Yes.
Dwayne the Croc Johnson.
Oh, I thought that was another one. I was like, oh.
I don't know why I have this, because this is literally what we just wrote. Okay? Right? So I'm being redundant. Perfect. Write this down. Okay, so our function is e to the negative 2x. What's f of 0? Okay, our derivative would be negative 2 e to the negative 2x. Our derivative evaluated at 0. Our second derivative would be 4 e to the negative 2x. Evaluated at 0 would be 4. Do we have enough of a pattern? What?
Yes.
Okay. What would our next derivative be? Negative 8. Okay. So, e to the negative 2x would be 1 minus 2x plus 4 over 2 factorial x squared minus 8 over 3 factorial x cubed. What would our next derivative be? Okay. So what's our pattern here?
2 to the k. Negative 2 to the k.
Negative 2 to a power.
X to the power over.
Okay. So negative 2x is being raised to the n power over n factorial. Okay. So we can write that e to the negative 2x is the sum from n equals 0 to infinity of negative 2x to the n over n factorial. What?
We're just writing functions as series.
Yes. I'm going to skip that example. Okay. Now, what is nice is we have some functions that make nice patterns. Okay. E to the x is one of those. Cosine of x is one of those. Sine of x is one of those. So we're going to write down 3 series that I want you to remember. Okay, I want you to remember their patterns so that we can use those to our advantage when I give you other polynomials to work with. Okay, so e to the x. Our function evaluated at 0 is 1. Our derivative is e to the x. Our second derivative is e to the x. Our third derivative is e to the x. right? Every derivative is going to be 1. So what's our pattern?
X.
Remember that, because I'll show you what you can do with it instead of what we just did for that example. Okay, cosine of x. When we evaluate, well, let's just go through it. The cosine of 0 is, okay, well then our derivative is negative sine of x, and that is 0. Our second derivative is negative cosine of x. And then our third derivative, we'd be back to sine of x. Our fourth derivative would be cosine x. So we are going to miss every other term because we go from sine to cosine, sine to cosine, sine to cosine with some negatives happening in there, right? But the sine of 0 is 0. So anytime we have sine or negative sine, we wouldn't have a term. Okay, so let's describe this pattern right here. Well, we alternate, right? So negative 1 to the n. What else?
X to the 2n.
X to the 2n over. How about 2 in factorial? Since our power matches our factorial. Okay. Okay, sine of x. Okay, same kind of thing happens, right? But which ones are we going to have? The odds. The sine of 0 is 0, so we don't have a constant term. We take the derivative to get cosine, so we would have 1x. We take that derivative and we have negative sine x. We take that derivative, we have negative cosine. Okay, and that pattern is going to continue to where we only have the odd powers, but we will still alternate signs because of the relationship with sine and cosine and their derivatives. Okay, so let's describe this pattern. We have the alternating piece, but now what is our power on x? 2n plus 1, and that matches the denominator's factorial. So what we're going to do is I'm going to have you remember these, and then in the case of like e to the negative 2x, we could just come over here to e to the x and replace all of the x's with negative 2x. And we don't have to go through the whole process again. Okay, now if it's not one of these special functions, then you'll have to go through the Taylor polynomial process and figure out the pattern, but that's okay. I have faith in you, okay? But if it's a combination or just one of these functions, then we can use these to help us, okay? So what can we do with these functions and their Taylor series? So like I just mentioned with our first example, we can substitute into a series for x. So if you have like the cosine of 5x, you can take the series that we just wrote down and replace all of the x's with 5x. Or if you have like e to the x plus 1, all right, you can substitute all in those, all for the x plus 1s. You are allowed to multiply or divide by a constant and or a variable as an x. Okay? We can multiply or divide by a constant or a variable.
Is there anything we can multiply? I was about to say, like, isn't that everything?
Well, you wouldn't multiply.
Is it a constant or a variable? Like, not multiple constants? Or multiple constants wouldn't matter, but multiple variables.
Multivariate.
I mean, you pretty much have a lot of liberty. Yeah.
Can you add or subtract? Oh.
You read my mind, Joe. You can add or subtract two series together. We are in calculus.
So we can take this.
We can differentiate or integrate a series, but remember this could change the interval of convergence while the radius would stay the same. Pretty much everything's coming into play in this chapter. And don't forget what we've been practicing. We can recognize the series as a sum of a geometric power series and be able to write it down. Okay. So we're going to do 3 examples where we get to use a variety of these methods. Okay. You'll have homework tonight. Tomorrow we'll have more problems to work on in addition to some extra problems based on our 2 previous sections, 9-8 and 9-9. So you can prepare for your quiz on Monday. Okay. I know, I don't like it any more than you do. But I didn't want to rush this section or the 9.9 section because I really felt you needed the practice yesterday. Okay, and I think you would agree? Yeah. Okay. Yeah. Do I have them? I have them.
Do you have them graded?
No. Well, Lily hasn't taken hers anyway, so I
I'm
can't get them.
taking it today.
Really?
Sorry. Not
Very
really.
sad.
That function was like really fun before we started doing the series.
I think I've gotten like 3 something.
Okay. So this is what we get to do. We know that the sine of x, I'm just going to rewrite this here for you, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. That's sine of x. So, if we want sine of x squared, yes, all of the x's become x squared. In your terms, that's a 2. Oh, what am I doing? That's a 2. And your general term. Okay, I ask that you simplify it. Now, in the instructions, I could ask you for the series, or I could ask you for the first 3 non-zero terms and the general term. Here I have written, but not simplified, the first 4 non-zero terms and the nth term. Okay? What I would want from you, though, is I would want you to write this as x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. And then with our general term, power to a power you multiply, so this becomes x to the 4n plus 2.
But you don't have to edit the factorial.
No, it stays the same because it doesn't get affected
Okay.
by the square. Yes,
If that's the nth term, why do you do plus stuff?
because it's an infinite sum.
And plus one.
But this is the general term. All of your terms look like this, where n is, 0, 1, 2, 3. Yeah. Okay.
Uh-oh.
Why do you say uh-oh? Move it out. Out of what? Okay, well, first of all, please imagine doing derivative after derivative after derivative for this Taylor polynomial.
No.
We all can agree that that would stink.
No.
However, we know that the cosine of x can be written as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Oops, an extra dot. Okay, this is how cosine could be written. Okay, and I'm writing right now the first 3 non-zero terms and the general term. Okay. Okay, so now what do we do with x? Distribute it through. So we would have x minus x cubed over 2 factorial plus x to the 5th over 4 factorial. And we do the same thing with our general term. This would become 2n plus 1 because we're multiplying x to the 1st with x to the 2n. So here are the first 3 non-zero terms and the general term for x cosine x. And I could ask you for the interval of convergence if I wanted to, right? And we would do the ratio test on that guy. What, my dear? Gabe?
Well, I was saying that I agree with it.
You don't want to do that? I will make you today.
Yay.
But in an AP problem, they would probably ask you to find the, like they could say, find the first 3 non-zero terms and the general term for x cosine of x. Part B, find the interval of convergence for x cosine of x. Part C,
Find the
blah,
10th
blah, 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 blah,
derivative.
blah, blah.
Find the 10th derivative of the series.
What?
To find the concavity of the 8th derivative.
The concavity of the 8th derivative?
Yeah.
You're out of control, Joe.
If you need the concavity of the 8th derivative, just take it to the 10th derivative.
Okay. What's your max?
3 derivatives.
Oh,
That's
okay.
not any more, then I'll just say no thank you.
But we'd have to take the fourth derivative to
No,
find that
thank you.
max
No,
of the
thank
third
you.
derivative.
No, thank you. No, thanks.
I like the fifth derivative because then I write it as tally marks and I cross it through. I did that in the
You don't actually do that.
That is
Roman
intellectual.
numerals.
Okay, so I'm gonna write 1/2 times instead of over 2 because I don't want to make that really long division bar. Is that okay?
Yes.
Okay.
We're gonna line all across the street. That's a big issue.
It wouldn't be very straight and it would bother me. So I've also passed on apparently my tendencies to my children. Yesterday was Wacky Wednesday, and my 5-year-old would not dress wacky. Like, you get to mismatch. I don't want to. Okay. Go ahead. Do you want to do it? It's like Dr. Seuss week. Did you know that? Because it's Dr. Seuss's birthday.
I remember that.
I haven't seen the musical process.
You haven't seen what?
I haven't seen the Google Doodle yet, so I would be
All right, so e to the x we know is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Oh, I'm going to have to write small. That's e to the x. And we are adding e to the negative x. Okay, what's going to happen when we plug in negative x for our e to the x series? Okay, the odds are going to become negative, but the evens are going to stay as is. Do you agree? So-
we just remove the odds from existence on the other side.
Snap your fingers.
Dang it, I was just going to say that. You beat me to it. I was going to finish writing, so I didn't make a mistake.
Things that
I mean, apparently
Captain Marvel comes out March 8th.
next week, that's what I thought.
That is a week from
it
tomorrow.
already has bad reviews.
What?
I don't know how that happened.
I don't know how that's
I mean,
possible.
that sounds about right.
I
Who?
mean,
What?
Movies giving movies bad
We
reviews.
talked about that neighbor yesterday.
Look
Her
at extra.
husband is in the movie. He's a security.
Oh, yeah. 'Cause she has the
She has a
poster.
poster like signed by him on
Okay.
her door.
I'm watching out for this now.
So, okay. So Joe snaps his fingers,
yeah,
and all of the odds
are gone.
are going to cancel out.
But all the evens are gonna double.
Oh.
But
Okay.
And then the
One half.
math gets
Hold on. You guys are just upset.
Thanos does a triple snap.
Okay. So 1 plus 1 is 2.
Whoa.
X squared over 2 factorial plus x squared over 2 factorial.
So much better. You know the quadratic formula was
Everybody's pretty in their own way.
Okay. So you crazy cats. Can we all agree that the odd powers are going to go away, and then we have 2 of all of the even powers? Let's write that general term then. Do we have any alternating?
No.
No. But we would have x to the 2n times 2 over 2n factorial. Because we have 0, 2, 4, 6.
Okay, would you have to write that step, or could you just?
You would need to write that step. You would need to write this step, and we have to write it based on what we have here. We can't really like add these together, right? We have to look at the pattern here, okay, for the general term. But we need to write it so now that we can just multiply that 1/2 through. And it makes that general term nice because when we multiply that 1/2 through, it just cancels out with the 2. And voila.
Would you just add the two together and then just take out x to the n over n factorial, and you have a 1 plus negative 1 to the n?
Which is 2. Yes, you could. Probably more work than looking at your pattern. But you're right. You could add them together and do some factoring and thinking and go from there. You're right. Thinking. That's the key. That the thinking is what we have to be careful with, right?
Thinking is
That's
Okay. We're gonna go back to that example, and I'm gonna stretch your brains a little bit.
hard.
I wasn't ready to stretch them earlier, but we're gonna do it now. This is pi.
Man, I don't even know what that symbol is. Brain's really
Yeah.
gonna get
That's
stressed.
the symbol that pops up when you're in Notepad and you try to use like control shift. It's really
No, that's the symbol when you open an image in Notepad. You ever just open a
Sorry, we're looking at like 2050 over here.
You ever just open an image in Notepad?
What situation?
So f of x is sine of x, and we're centered at pi over 4, so we can't use the sine of x shortcut
Oh, that's upsetting.
because that's only when it's
Oh,
centered
that
at.
is zero.
Sorry,
I need to write that down.
I don't feel like you're actually sorry.
you need to write down that they're centered at 0.
I feel like that's so much.
Okay, I saw C equals and then I automatically went to derivatives.
Okay, because here we're going to get values for every derivative because we are centered at pi over 4, right? Our first derivative is cosine of x. Evaluated at pi over 4 is radical 2 over 2. Do you think that we're smart enough to figure out that this is going to go radical 2 over 2, radical 2 over 2,
Negative.
so positive, positive, negative, negative, positive, positive, negative, negative, and they're always going to be radical 2 over 2. Are we smart enough to figure that out?
Yeah.
Good.
Who said
So-
that, Barbie?
We have radical 2 over 2 plus radical 2 over 2 x minus pi over 4 plus, oh, what's the easiest way to write this? Radical 2 over 2 factorial x. Is that enough? You think? Do you want one more?
No. This is enough.
What do they all have in common?
Radical 2 over 2.
So do we factor that out?
What?
What?
Oh, you just factored it out. Okay, I thought that was the general term for it.
Why did you add the first term and subtract the next two?
Because that's
Positive.
positive, negative, positive.
Can we random general term for this? What do we do?
Patterns, guys. What would start with?
Okay.
We need negative 1 to a power.
Negative 1 to the floor function of n over 2.
If n is over 2, then negative 1 is n equals
0.
1.
1. But 2 over 2 would be 1. That would be negative 3.
But I don't want to put a floor.
Without using a floor function.
I don't want to use I, because if negative 1 to the 1 half gets involved, then
No, it's a
I.
floor function, so it's rounded down.
No, don't.
Don't, he says. That's it. Just don't.
That's fair.
I don't think.
Okay, without a floor function, can we get positive, positive, negative, negative, positive, positive, negative, negative?
Negative 1 to the n times negative 1 to the 2n.
So negative
We could always write two different series where one of them's always odd, the other one's always even.
What would that? Well, what would that do?
Oh, that looks like something.
Tell me the pattern. When you plug in 0, we would get.
You would get positive.
Okay. When you plug in 1.
You would get
One.
negative. Yeah, positive.
2, 3,
And now n equals 1 would be negative 1 to the first, so then you can go.
No, you can still 1.
Okay. What about 3?
So it would be
4? We're getting the positive, positive, negative, negative, positive, positive, negative, negative. Oh, that's not right there. So this is what we're gonna do.
I have to start at negative 1.
We're gonna add 1 to the series to account for this guy right here. And what I underline in red is what we're going to write. No way. I wasn't even gonna do this example.
Just be on the test.
No.
What is the,
It will be on the list, right?
what is the n times n plus 1 over 2 from? That's a pattern for something, isn't it?
It's a pattern for positive, negative, negative, positive.
Sorry.
I don't know what.
If the 1 is
That's a
inside the
formula
series,
for something.
then
Oh
Isn't
yes.
it?
shouldn't the 1 be
Um,
added outside of the series so that not every
The sum of the integers, consecutive integers, like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7.
Okay.
Something like that, yeah. I just need to know that I have seen
Yeah.
it.
How do you figure that out? Like,
Joe.
Shouldn't the plus 1 be outside of the series, otherwise 1 will be added to every term?
yes. Couldn't you also take two series, one where everything's odd and one where everything's even, and then add them together because then they both be alternating?
Oh, I see what you mean.
The odds alternate.
Yeah. Yeah. Okay.
Sounds like slightly less work, but it's also probably it's less thinking, more work.
Yes. Agreed. Okay, I'm not going to make you come up with something like this. I just wanted to look at a challenging problem because
You
I
have
want you to be
do
challenged.
Would that be on AP exam?
no.
Oh.
So, Hannah. Okay, Hannah will send you the picture of the homework, and please try one problem before you leave.
my school. This is my
Sure.
school.